All right. So today we're going to be continuing off of the April 22nd and April 27th lectures about amines. And then I can hear you, Barca. Oh, okay, there. It's unmuted. It's muted again. And then also, we're going to do a little bit of retrosynthesis and some other questions, but I highly encourage everyone to finish this by tomorrow or by Sunday so that we can go over any questions anyone has. This is going to be really tough material. So let's start with our amines again. So we have different kinds of amines. We have primary, secondary, and tertiary amines. We also, looks like we have quaternary amines, but those have a charge on them. And then there's ammonia. So ammonia is NH3, I believe. And I think ammonium is the one that's 4. Let me just check real quick. Ammonia is, yeah, NH3. And it is neutral. So as you know, nitrogen likes to be attached to 3 things. So then we also have a primary nitrogen, which is basically carbon, nitrogen, 2 hydrogens. Then we have secondary nitrogen, which is a nitrogen attached to 2 carbons and a hydrogen. Then we have a tertiary nitrogen, which is just attached to 3 carbons. Quaternary nitrogens are also possible, but it will have a plus charge on them. Okay, so these all have different names. The names are, there's a few different names with amines that we can use. So a butylamine is basically, it looks like this, and you can think of it in terms of tert because of the structure that we're so aware of, and but because it has 4 carbons altogether, and amine because there's an amine there. Then we have triethylamine, which is just, and it's just triethylamine, i.e. it has 3 ethyls in it. I can hear something. Hello? Can you hear that? Okay. I can hear something. Your phone. Okay. And then there's N-dimethylcyclohexylamine. So it's a cyclohexane that has an amine, a tertiary amine on it. And I'm not quite sure about how the naming works, but probably just memorize it or figure out a way that makes sense to you. It does have a dimethyl on the nitrogen, and there's also a cyclohexene, and yeah. So after that, let's talk about some different properties of amines. So first, in terms of structure and bonding, so the nitrogens are pretty much always going to be, they're either going to be sp2 or sp3, but depending on how, because like you can have a nitrogen that is attached to 2 on one side, and so that would be, you know, sp2 instead. And like the nitrogens, they usually have like a lone pair there. So then in terms of acidity or basicity, as you know, he talks about like resonance. So if there's one that has resonance in it and it has an NH2, that's going to be more acidic than something that's just a chain with an NH2, right? So it's more acidic. And then also when we're talking about resonance, it's important to note something about aromatacity. So we have the structure here with a hydrogen and a lone pair, and then have another one with, okay, with a nitrogen like this and a lone pair. So in this situation, when we're comparing acidity or basicity, this nitrogen is 2, and this nitrogen is P3, right? Because on the left side, we have a nitrogen that's attached to 3 things and has a lone pair, but on the right, it's only attached to 2 things and has a lone pair. So that means that this one is more acidic. I.e., if there was a hydrogen there, it would have been more likely to let go of that hydrogen. And then, and like this is just from what we know, the more S's we have in relation to P's, the more acidic, right? Okay, so moving on. Amines, similarly to when we're reacting, so remember how we spent a lot of time talking about this kind of structure in the last lecture. But in this lecture, we're going to be moving more on to this structure. So just think of it, instead of the O being there, it's a nitrogen. These are amides. So if we have this here, there can also be a resonance between the lone pairs that will cause a flipping of different kinds of molecules and stuff, like a resonance. So we can go back and forth between this and this. Okay, so there's like a back and forth thing there. And I think this might be important later for certain mechanisms. Okay, what else do we have? So so preparation of amines by alkylation of ammonia. So basically, how do we make our amines? And again, an amine is just a way of attaching a carbon onto a nitrogen. So what you have to do is you have to start off with 2 NH2s, or NH3s, sorry. And then you're reacting these with something, and we're going to note this R with a halogen on it. So the halogen is obviously going to break off, and the lone pair from the nitrogen, because as we know, nitrogens are attached to 3 things, but then they also have a lone pair. So this lone pair is going to reach out and grab the R, or the alkyl group. And this is just kind of just treat it like an oxygen. Oxygens always do that. So then what we end up is we end up NH2 with an R on it. And so we've let go of one of our hydrogens because of like maintaining octets. And what happens is that this also is accompanied by the other NH3, but now it's an NH4, and it has the halogen on it. Okay, so why is this important? Because in order for it to take the halogen has a negative charge. So the ammonia itself has to have a positive charge, right? So that's why this took one of the hydrogens. Next, we're just going to go from here. We're just going to continue the same exact pathway, but I'm going to forget about drawing this portion from now on because it's all going to be the exact same. So you react this with another Rx. Same thing's going to happen. It like the exact same thing. Although you actually have to react it with another, you have to react it with NH3 and an Rx, because that NH3 needs to be able to take away the lone pair, or sorry, it needs to be able to bond with the halogen. In the end of the day, we can continue the hydrogens from the NH3, the original NH3, to the point where we get to you know, possibly 3, or even you could get 3 like this, or you could possibly even get like 4 of them. Positive charge. So you can just continue putting alkyls onto your ammonia. And that is how you produce your amines. So not too bad, honestly. Like, it's just a pretty simple reaction. All you need to do is make sure that you have an extra ammonia there and a primary or some kind of halogen that can protonate. All right, so now we're going on to Gabriel synthesis. So Gabriel synthesis is just going to be another way of adding more more nitrogens, I believe, into the same thing, or adding more alkyls into a group. So first we start off with this structure. And this is going to be reacting with KOH. KOH is just a strong base. And so what it's going to do is it's actually going to create, and it's going to take away this hydrogen right here from the nitrogen. So base that takes the hydrogen. Actually, I should write, because that's not very obvious what I'm talking about. Strong base comes and attacks the hydrogen, so then we get a negative charged nitrogen in that position. So then this has a negative charge. After that, all we have to do is add on the alkyl of choice. So you could add on whatever you want. I might just add on like this with a halogen on it, of course. So the halogen is going to protonate spontaneously. Negative charge is going to come attack that. And so now we have the alkylation. And then from here, we have a neutral nitrogen that's attached to 2 carbons as well. And then at that point, if this is your desired end, you could do this. But also other specials that we haven't learned about yet, which is to use NH2NH2. And so what NH2NH2 does is it's going to kind of, I believe it basically inserts another NH on the, wait, is it supposed to be just an NH? Oh yeah, NH. So what it does, it'll insert another N. And it will also like break off the alkyl there. So this becomes, and these have to be 1 hydrogen each because they need to be attached to 3 things. Obviously, still have a lone pair each. And then the other one is broken off with an NH on it. So now this one is a lone pair. So it's like you took this essentially and replaced it with 2 N's. Think of it that way. So break this off and then insert in its place 2 nitrogens. And so the result here is going to be NH2. Okay, so that's a really important step that we'll talk about a little bit more. So how do we work with amines? So let's say that, and this is just, you know, other stuff kind of moving on to our, like, the basics of what we normally do. It is a benzene ring, and it has a primary bromide on it, a primary halogen. So if we want to change that to an amine eventually, we would first have to change it to an azide, right? So Na3 is how you get the azide, which is going to look like this, N3. Then from the azide, you can go to the amide by doing LAH. It's really cool. And then also, So really, there's no way to go straight from a bromine to an amide. You have to have that azide intermediate. But sometimes you want to stop at the azide for specific reasons. And then there's actually, this isn't the only method of going about that. There's another one. You can use a nitrile as an intermediate. So again, if you have your bromide in this position, you can react this with NaCN, and that will give you your nitrile intermediate. And then you just use H2 and Ni, and this is at 100 ATM. I don't know if all this will be exactly necessary in order to get full credits. And what that yields is the same thing as above. So here are two different methods. Sometimes you're going to start off with a CN, so you know you need to use this method. And sometimes you're going to start off with a nitrile, so you need to use the LAH method. But if you start off with a halogen, then you can use either one you want. So let's do another practice of the Gabriel synthesis. So here's the same kind of problem. We're just going over one more time. So I think the way, and I don't really know, like, I'm not fully aware of the entire purpose of these Gabriel synthesis, because in this situation, what he's showing is that first we're reacting with Cl, and as we know, this is just going to give us the same thing, but there's going to be that many carbons attached to it. I'm not even sure if that number is right, but you get the point. And then what happens after this is that we're reacting it with NH2, NH2, which is the whole, you know, Gabriel, hallmark of the Gabriel synthesis. And he shows as the product here, which is a very interesting thing, is he shows the product is NH2. It's the same thing with NH2. And I'm looking at this like, if the whole purpose of doing Gabriel synthesis was to get the product, you could have easily done that with just you know, Cl and then you know, NaCN. You could go that pathway. The pathways we just talked about, right? Those are great ways of turning a bromide into NH2. So I guess in the end of the day, like, I'm not quite sure. Maybe if he gave you starting point, you would need to go this route, because you know, it's not always you're given the right materials to just go through this. But what I will say is that I never know, because this isn't like an actual, like, we don't actually do organic chemistry in undergrad essentially, and so we don't know, like, there might be some very strong laboratory reason to do Gabriel synthesis over the other ones, and maybe because it involves like a lot more steps and stuff. Okay, so synthesis of amines from nitroarenes. So this is just continuing how to synthesize amines. So we've talked about several methods above how to synthesize amines, and here is the fourth one we're going to be discussing. So if you have a aromatic ring, like a toluene, for example, all you have to do is have, and we've learned this before, HNO3 and H2SO4 will yield a para addition of an NO2. Okay, this is already, we've learned this. From there, all we have to do is use, and I think this one is new, there's lots of different options for this, so please look at the notes, but I'm going to use FeHCl and NaOH. And all this is going to do is going to change that NO2 into an NH2. And so what's the significance of this one? Well, it is an aromatic ring, and that's kind of necessary in this problem, that it's an aromatic ring, because this HNO3 portion that we talked about, that's back from exam 1 when we learned about adding onto aromatic rings. Okay. And then we have a few more syntheses. This time we're going to be talking about, we're going to continue talking about amines a little bit. one way of turning an acid into an amine. So you have your acid here. What you have to do is a coupling reaction, and all that's going to do is it's going to turn the OH into a Cl. So when you use SOCl2, and you just put it all in one step, but it's important to know what each of these steps means. So SOCl2, and then also he's using this. And so the SOCl2 will just take out the OH and replace it with a Cl. And then NH2 will react with that just the way we've learned of when there's a halogen, then the halogen protonate and the NH can attack there. So what we end up with after this step altogether is we end up with our nitrogen here and it's the two methyls. And then what he's saying is that from this point, all you have to do is LAH to get rid of that altogether. So it looks like LAH is turning out to have a lot more uses than we originally learned about. And I think in this case, because of how the nitrogen is adjacent to it, that will cause the oxygen to just completely leave. So originally what we learned about was that if you have a meal like this and you react it with LAH, you can expect your product to look like this, right? But I think that having nitrogen here is what really makes a special reaction where it ends up with the OH completely gone. Okay, so this is the difference between the two of them. So again, just don't use LH exactly the same way as before. You can normally, but when there's an amine there, you have to be careful and remember that LH has some different functions with amines. Okay. So then there's also a method for replacing a carbonyl with an amine altogether, okay? And there's also our Whitting-like reaction, so we're going to go over a few of those. So firstly, one weird reaction is if you have a ketone and you react this with NH3, then what'll happen is that you get the replacement of this oxygen with an N. And it might seem kind of weird, but this is exactly the same problem we've done before with those I don't want to call them Whitting reactions because they don't involve an elide, but Whitting-like reactions. If you remember when we talked about something that has a double bond and we react it with, I don't know, a nitrogen that looks like this, remember? Something like that. And what we end up with is we end up leaving that double bond. And I said, take that O, erase the O, replace it with a nitrogen, then draw the rest of the thing around it. Then, because it's breaking octets, take one of these lone pairs, put it into a more favorable position. So it's very similar problem. The only difference is that it's going to have the alkyl groups attached to it. So in the end of the day, it's not a weird reaction at all. All right. We're going to look at a few more of those reactions. They're not crazy. You've seen them before. So we start off with another ketone, and this time, and then by the way. So after this, you can do another reaction with H2 nickel and ETOH, and that'll give us this being changed to just an NH2. So it takes away that double bond. Oh, NH2. It takes away that double bond. And honestly, when I look at this one, I just think about how H2 is usually used to remove double bonds anyways, right? We always use H2 to remove double bonds or triple bonds or whatever. And so it's not that weird at all. Just remember the nickel and the ETOH, that's pretty important in eliminating that double bond. So going back to this next problem, we're going to react this with an aromatic ring that has NH2 on it. And this is just the same thing. It's super simple. So all you're going to do is you're going to take your original drawing and put everything on it. Just erase that oxygen and replace it with the nitrogen. And obviously, I'm going to have to flip everything upside down a little bit. But what we're going to end up with is like this, right? And that original H that was there needs to be gone because of octet. So you can always get rid of hydrogens that are on the nitrogen, but you can't just get rid of other carbons that are on it. So from this point, once we react this with the second thing, which is nickel, ETOH, what's going to happen is that if we look back at like what this even did in the first place, is it's going to take away that double bond that is there on the nitrogen. So I'm just going to draw this, the nitrogen, just draw the exact same thing of whatever. And then instead of having the two there, just take away one of the double bonds. Now, what you're going to notice is that our octet isn't filled anymore, so you're going to need to add one more hydrogen in this case. So in general, with these problems, once you do this step right here, you're going to have to, which is the new step from this unit, because all the other stuff was from before, you're going to have to, essentially, you're going to have to take away the double bond and add a nitrogen. Or sorry, add a hydrogen onto nitrogen in replacement of that double bond. Usually. I wouldn't take that as a rule of thumb, like all the time, but you can still kind of know it, you know? Okay. All right. I think that's it from what I'm seeing. So let's go on to, okay. Oh, we're nearly done with the lecture. Yeah, there's not much for the final material. It is going to be tough though. So here we have the Hoffman elimination. So a Hoffman elimination is basically a drug. We have a nitrogen with a positive charge and also an OH to balance that with a negative charge. So it's a salt essentially. That salt, we'll learn how to form it in just a second, how to form this actual salt. But what happens to this is when you have it with heat, it's just going to create an elimination. Just think about protonating all this and creating an elimination. It's not maybe the exact mechanism, but it is going to be helpful for you. So just eliminate it. Oh wait, no. Eliminate it to the, it's because it's very hindered and stuff. So eliminate it to the side. Like you notice that I put it on this side and not in the middle, which is your normal instinct. How do we form this? There's a whole bunch of steps, but what I will say is that this is the important thing to know. There's a whole bunch of steps to form this thing, right? If you just start off with an NH2 in that position, and then react that with like something with a that protonates. So here he used CH3I, and there's excess of this. Then you react it with Ag. This is really, really important. Ag2O and H2O. Then you react it with heat. You'll get that elimination. So why just do all these steps, bunch them together? Because there's no point in drawing out each of these little steps where it becomes like a salt and then all that kind of stuff. But right at the point, it is a salt. And this step is to just add on a whole bunch of, so if you want to know each of the steps, that first step is just to add on a whole bunch of those methyls, as many as possible. So we'll add on 4 of them and it'll have a positive charge. The AgO2O is to turn it into a salt. So it'll just turn that into the same thing, but it'll have an OH next to it. And then the heat is for eliminating it. But all of this is like, really, you don't need to know it. The main point is you just start off your NH2, you do each of these steps, and it will result in an elimination. But remember, this elimination, because it's so hindered, the end product is so hindered. Look at it. It's a nitrogen that has 4 carbons attached to it, in addition to probably a lone pair as well. Or wait, no, it doesn't have a lone pair. But yes, so having that many will make it, now I'm curious. 1, 2, Okay. So anyways, yeah, no, so no lone pair. But anyway, yeah, so anyways, it's super, super hindered, and so it won't be able to eliminate according to Zaitsev's rule or whatever else you prefer. It's just going to go to the side that's the least hindered. Okay, so going back off of something else that we talked about. So I don't know, this what it could have been up in the portion, but think about it if you have an aromatic ring. Now, how are we going to start adding our nitrogens on? The best way is to H3, right? And we've already talked about this with H2SO4. We've already talked about this before. It's just a way of something that we learned from the first exam of adding a nitrogen onto an aromatic ring. It'll add an NO2. After that, to change that into an NH2, we can do FeH cell OH. And that will change that into an NH2 instead of an NO2. But then, this is the new part. So the next step we can take is to react this with, and this one's a little bit complicated, NaNO2, H2SO4, H2O, and then basically cold. And what that'll do is it'll give us nitrogen that's triple bonded to another nitrogen. And I don't even know how to pronounce these, so but don't have a positive charge. So this is the results from that, right? If you see N2, okay? So what that'll look like is, because you're not always seeing the bond line structure, if it says like N2 plus, that's what this is. And that's how you create it. You have to start out with an NH2. In order to have an NH2, you could have either gone the NO2 or the CN route. Either one will work. So let's just do a quick review that he has here. And remember, so no, not a quick review. So once you have your N2, there are so many different things that you could actually end up doing, and it's kind of, oh wait, yeah. So firstly, let's just go back to the beginning a little bit. So NH2, all we have to do is react this with NaNO2 and H2SO4. So it looks like there's a slightly shorter version. He didn't add the H2O when they're cold, so I'm assuming you do not have to include that every time you do it. What that'll produce is it'll produce this with an N2 and a positive charge. Now from here, there's endless things you can do. So let's talk about them. The first thing you could do is you could react it with CuCl, and that'll just change it to a Cl. Okay. The second thing you do is CuBr. So this is just your halogens, right? Same thing, Br. Then we have CuCN, and that'll change it to, I'm going to change the orientation a little bit to fit them. That'll change it to a CN. You can also react that with H2O and heat, and that'll give you OH and alcohol in that position. You could also do, this one is new, H2PO2, oh, H3, sorry, H3PO2, and that will give you a complete removal of everything, so just back to an aromatic ring. Or finally, you could do Ki, which is just another like halogen. That will give you an I in that position. So, oh, and for this one, you could do this, or you could do, it looks like a simple base will do it. A weak base will do it. Either one will remove that completely. I think the reason the weak base will do it is because it will take that nitrogen away and it'll be gone. So these are some of the methods for things you can do after you've gone to N2. So just to remind you, there are several ways of getting to these methods. First step is you could start out with the halogen. Seems very necessary in general if you're going to have to create any of these. So you start off with a halogen, and then from there you can get, you could either go a CN, or you could go a H2. Oh, sorry, NO2. But either way, from both of these, you can get back to a NH2. And then from there, you can go to an O2. And then, you know, from there, any of those things are possible. I mean, some of them are a little bit crazy. Like, why would you go from a BR all the way back to, you know, another BR? Like that. There's other things that are possible. Or like, why would you go the step of going BR, CN, only end up as a CN? So just, you know, just keep these like charts in mind, keep all that in mind, and then use it when it's helpful. All right, I'm trying to figure out if there's anything else we need. Okay, no, that's the end of that lecture. We pretty much finished everything. So, do you have any questions? Anything that's unclear that I could explain a little bit more about?
No.
Okay, cool. That wasn't too bad. I was expecting it to be a lot harder, but it really wasn't too bad. Let's do some retrosynthesis for a little bit of practice.
Okay. It seemed more difficult when I was doing it alone.
Yeah, and when you do it for the first time too, right? In the end of the day, this page right here is pretty much all you need. And then you just need to understand the basics of this one right here. This one's very important. And then your Gabriel synthesis. But other than that, the other stuff isn't actually new. Okay, so for retrosynthesis, let's try this one out. So we have an aromatic ring eventually becomes a secondary NH2. So when I'm looking this, I know that there was a carbon added at some point. How was this carbon added? Well, so when you add CN onto something, that's actually the addition of one more carbon, right? And so let me see something. Just want to make sure we did this. I find the use of LAH has changed a lot. So here are some of the LAH things I'm going to want to highlight because I just really want to review LAH with everyone to make sure that we're all good on that. Okay. So the first time we saw LAH was here. So that LAH can turn an NH3 into an N3 into NH2. Then we saw that it can also completely remove a double bonded O. Right. Like completely remove it, not reduce it to an alcohol, just remove it entirely. And then was that it? Yeah, that's it. Okay. But in here there's gonna be a new use, so I guess I must have missed it somehow. Or maybe we knew this from before. So when you have a CN, you can just use LAH to turn it into an NH2. Oh wait, no, we didn't know that. We literally, that was the first step we did right here. Yeah. Or wait, no. Oh, okay. I get it. So this step right here, where you pass CN and then you go to NH2, that's essentially LAH. LAH is such a similar molecule to H2. So that's very similar to LAH. And I think the takeaway here that I'm getting look at this retrosynthesis is that you could use LAH either way. You could use LAH to get from the CN to the NH2. So knowing that, there's an easy way to get from a CN to an LH2, right? And that would just be using LH. So we know that there needs to be a CN in that position. How do we get a CN into that position? Well, we need to start by adding something onto the aromatic ring. So he in the answer, he went straight to adding an NO2. You could easily do that, or you could add a bromine first. But he just went HNO3 and H2SO4 because there's like a really easy way of just starting out at NO2. So once we're here at NO2, we have to change this NO2 into an NH2. And so going back up to what I highlighted, if you have, oh wait, no, that's not NO2. Where's the aromatic ring example? NO2 to NH2, oops. You can use this. FeCl, NaOH. Or it looks like this he used here in the retrosynthesis, because I just want to use things we talked about. In the retrosynthesis, also use H2 and nickel to get from an NO2 to an NOH. Sorry, an NH2. And then from here, we just have to be able to get to a CN. So let me go back. I actually don't really like this method much, but I'll show you. Because here we learned that to get to a CN, you can just go straight from a bromine, and that would have been my first instinct, to just attach a bromine on first, because that's super simple. But then NH2, where are we? This list over here. We saw that once we're at NH2, we have to go to N2 with a positive charge. So that is accomplished with NaNO2 and H2SO4. That will be acceptable. So NaNO2, H2SO4, that gives the N2 positive charge. Then we can go to our CN. So I think this is a little bit of a long way around, because what I'll show you in a second makes sense. And I think the reason he's showing the long way around is because it'll just get a better grasp of like so many things that are happening. But we have LH and H2O. Okay, so what I was thinking is, obviously if you start with a bromination, that would be way easier. So you just go like Fe Br3, Br2. And then that will add a bromine somewhere. And then from there, you just have to turn it into a CN with NaCN. And then from there, just LAH. And this is obviously way easier. But I think that, once you've gone to an NO2, it's pretty much impossible to get back to a CN unless you go through all the steps of ending up at an N2, like we showed in the charts up here. Ending up at an N2, and then when you're here at the N2, you're going to choose the method that ends you CN. Right? And when they say CuCN, you can obviously use NaCN. That will still work. Okay, so yeah, I think that, that's obviously a very complicated way of doing it. You would get full points if you did that, but it's good practice. Okay, so the next problem is stereospecific. And okay, so this is what we have. This is not quite correct.
What?
All right, so what's going to happen is we're going to get here to a solid NH2, and the exact same thing on the other side. So the main difference here is we notice that we're doing a substitution where the OH becomes an NH2. And the best way to kind of do this would be to change. So the OH currently is not a good leaving group at all. And so what he's using here to remind you of how to leave it is actually a little bit of a review, and it's great to see it because it might come up. He's using TSCl. As you'll recall, TSCl looks like this. And what TSCl does, and that's besides the point, because, as soon as you see that, you should think TSCl, and just, it doesn't really need to be drawn out completely. What TSCl does is maintaining the current stereospecificity because it's not a substitution. It's actually just adding onto the actual O. It's not substituting onto the carbon. So it takes that H, probably removes the H, and what it replaces it is OTS. All right. So instead of TSCl, it's OTS. And this remains the same. Because guys, if you remember, with substitution, it usually becomes the opposite, right? So if something's in the back like this, something substituting on it will have to attack from the front, right? That's how SN2 works. So from here, then we're going to have to go to an NH2. How do we get NH2? Let's go back. So the best way to get to NH2 is either to go through a CN or an NO2. Either one will work. So here, I think either one is okay. Let's go the N. Seconds. I'm not sure how to substitute an N2 here. Oh wait, this one didn't relate. These are all in aromatic rings, so it's quite easier. Just put an NO2 there. All right, let's see. Yes, let's go to N3 first. All right, because that was the other method, N3. So to get an N3, we just do NaN3, right? So NaN3, and that will just substitute this. So now it becomes forward facing, which is our desired end product. And then we have that. Okay, so from here, we just have to change that to an NA2, which can be accomplished with LAH. And that's it. If you wanted to go the CN method, I think just using N at the end would work as well. Either one would be fine. Okay, so that's really it for, oh yeah, no, we have some more retrosynthesis down here. Let me do one more retrosynthesis problem. I feel like we're honestly ending now because no one's here to ask questions, so there's not much to go over. This one looks nice and fairly complicated. Okay, so here, oh, and also this other starting product is this, which is a nice hint. And this is great throwback to what we did yesterday for the beginning portion of this material. So what we have to do here is we have to somehow, wow, this one is complicated. So we need to somehow end up, obviously the ketone gets reduced, but that's easy with LAH or something. But we also need to have a acid as well. So what I'm thinking is actually doing this one backwards than to be done. So we can't actually use LAH. Our starting thing must have been right before this. We must have had this as like a double bond. And we know that like LAH would attack both the acid and the ketone. So to combat that, we're just going to use NaBH4. And that will attack just the ketone and not the acid. All right, so here we are. Now, interestingly, you'll see that this this group right here, right, including the carbon actually, that is just half this, right? Let me draw in a different color. So what I draw here in red, this is the same thing that I've circled in red here. And so interestingly, imagine if the alpha carbon here attacked this portion of the thing. That would result in this, right? And then we just have to cut off one of the acids. And then turn that acid into, or like the turn the ester into an acid. So this could come from something like this, where you have the alpha hydrogen attacking here, and just have that on each side. Okay, so once we're here, oh, it's an ethyl in reality. Okay, that helps. So how do we, and you know what, I like what he did. He's just going to change this to OET to make it a little bit cleaner because there's a lot going on. And so at this, so to get from this point to the other point, we number one have to cut off one of the esters, and number two, we have to change the other ester to an acid. To do that, you're going to use, the heat was the only thing for the second one. So you use KOH and H3O plus, and that'll take off the one ester, and then heat will change the other ester to an acid. Then how do we continue this passageway? So one thing I'm noticing is that there has to be like something here to make it want to attack this portion in particular. And so the way of doing that, yeah.
If I do BR2 over FeBr3, wouldn't it attach a Br in the meta position?
This is not an aromatic ring, so no.
Yeah.
Yeah, unfortunately. That would have been much easier. So, really, it's pretty complicated, but what we did know is that we can easily attach a bromine to an alpha position, right? And so if we utilize this alpha position and then eliminate it, we'll be able to work this out. So this is the alpha position of this molecule. So to utilize that alpha position, we're going to have to do first a bromination and then eliminate it and then have it attack the double bond. So to get the alpha halogenation, this is something we already talked about, and I know it's like hard, but we already talked about it. CH3CO2H, that will basically put an alpha halogen, a halogen in the alpha position. And then we can just eliminate that with, I don't know, whatever you want, you know. Let's go like this. And that will eliminate it. Now, from this position, so he just used one more base to get the, and but I'm using that other molecule with another strong base to get that to attach. And so you can think of the strong base, like what's the purpose of the strong base? Actually, no, that doesn't work. Oh yeah, what's the purpose of the strong base? The purpose of the strong base is to get rid of the alpha hydrogen so that it's now a negative charge, right? Because this is just sitting there like this. And the OET minus just comes along and attacks the alpha hydrogen. So that's the whole point of having that strong base. And then that alpha hydrogen will be ready to attack. It'll attack the double bond. Now, the only thing I'm having issues with is I don't really see this as a very clean reaction because, I mean, while it's going to be more likely to attack that carbon just because of hindrance, there is a chance it could attack the carbon right above it, right? So it has a choice. It can either go to this side or this side. And I think at the end of the day, with the stereo hindrance, it's going to be much, much more likely to come down to the bottom, which is the product we want. So again, very, very, very complicated retrosynthesis. Definitely pay attention to this one. I think in the end of the day, if you study all the retrosynthesis he gave you, it's not like he's going to give you something like this on the final and like you're going to have to figure it out right then and there. But definitely know the tougher ones that he's asking you, because he could ask very, very similar ones, like very similar though. So it's not like you're gonna have to completely make it up out of thin air. You'll have to recall some previous things. I think the hardest steps in this retrosynthesis, hardest steps to recognize are this one, where same kind of step, we can remove one of the esters and then turn the other ester into an acid. That's a really important step that will be hard to overlook. Another one is this step here, because in the end of the day, we don't really think of, when we usually think of an alpha hydrogen attacking something, we don't necessarily think of it attacking like a double bond, but it can. Usually we think of it as attacking a leaving group or something, but we didn't really have, I guess we could have tried to make it into a leaving group, but that would have been a lot of extra steps. And then finally, the other important thing to recognize is what I already circled in red, which is to look at that and see that that is actually half of the original start. We ended up with half of it, and so that's a really important step in figuring out this problem. All right, I am gonna do one more retrosynthesis. One more, and I think that's it for today. Again, we'll have Sunday, we'll have questions and answers. And so anyone's open to bring any questions there. I also might post, I'm thinking about posting like a better version of this chart right here, where I just include all the basics. So if I make that, I'll send it in the group. So in this retrosynthesis, we're starting off with 2 of these, and we're ending up with something very, very, very different at first glance. All right. So for this problem, we have to recognize what's extra here. Well, clearly, this aromatic ring came from somewhere else. This is definitely could not have been part of the original starting thing. All right, what else? So the hard thing about all of these is that recognizing shapes is going to be really important, because in the end of the day, with the manipulations we can do to certain esters and stuff, it can end up looking way different from where it started. But I can make the assumption, since he gives 2 of these, I'm going to assume that they both react together, and we all know how that goes. So first of all, you can just draw them both out. And the way that the reaction works, just as a reminder, is that one of the alpha hydrogens, which is a negative charge, attacks the carbonyl of another one. And so what does this give us? This gives us and then from this side, we're going to have, well, this is a little bit tough. Let's see. This is going to break off. I think something like this. I think's wrong. Sorry. Oh, yeah. No. Okay. I think this is it. Okay, yeah, that's it. So let me just erase all that other stuff, because that was just part of it. All right. So this is what we have to react the 2 of them, and this is just, oh yeah, you need a base to make this happen. So I don't know. All right. So then from here, we're gonna have to figure out, how does this shape relate to this shape? So I'm gonna change this up a little bit. going to draw it a little bit differently. 1, 2, 3, 4, 5, 6, 7. So nope, wrong position. Okay, and then there's going to be a carbonyl here, a methyl in between, a carbonyl here. Something is wrong. Something is very, very wrong. This is very interesting. Oh, I skipped one of them. Okay, never mind. Yes, so this is the correct answer. I skipped this carbon right here. Okay, so this is the product that we kind of had at this, and we figured out to this product. So looking at the overall shape, I see that this and this were clearly the two carbonyls, so those need to stay. The methyl is also quite clearly there. The only thing that is gone is this. That's the only thing that we need to get rid of. And also we need to be able to attach a, what is it? Okay. We need to be able to attach a benzene, but the benzene has to be attached to exactly where. So we need to attach benzene here. And it has to be not just a benzene, it has to be like a benzene with a methyl on it. So we need to attach it to that carbon. So actually, this is the perfect spot to attach the benzene now, because it is an alpha carbon to two carbonyls, so that's perfect. So let's utilize this. So first, you're going to need a strong acid to take away the alpha hydrogen, and then you're just going to need to attach the required benzene with one carbon on it, and then let's just have like a good leaving group there so that we can attack it. So that's going to give us, this is so complicated, I'm so sorry. That's going to give us this. Now from here, we're just going to need a couple more things. First, we're going to need to be able to take away that ester, and then also change both of those carbonyls into OHs. And actually, the only way to do this is just a simple LAH. And I'll tell you why, because the first hydrogen, when it attacks here, it's just going to cut off the O, right? And then it'll continue. And LAH, you can always assume when you write LAH, there's an excess. So it'll react with the ester, it'll change that, keep on reducing it down until it becomes an OH and just an alcohol, and the other one will also be reduced as well. So that part isn't too complicated. But it's kind of hard to see at first that LAH can take like a complete ester and just clip off like a ton of it and just turn it into an OH. It's kind of hard to see that. Okay, I think that's it for today. Barca, do you have any questions?
No.
Okay, cool. So in the end of the day, I think we've finished all of the material. It's not like I've gone over everything, but that's mostly your job to go over all of the questions and the practice materials and whatnot. And I will try to post this soon. And yeah, so see you on Monday.
Okay, bye bye. Thank you so much, Fatima.
Thank you.